Hello everybody, this is K. Rani, and in this video we are going to learn about inverse Laplace transformations. After learning about Laplace transformations and different kinds of functions for which we have applied Laplace transformations. Okay, so what is this inverse Laplace transform? So it is a quite opposite inverse operator for this Laplace operator, and it is denoted with L inverse. Okay, so inverse, the name itself gives a meaning. Inverse Laplace transform. It is an inverse function for this Laplace transform. So usually what we have done with this Laplace transform means Laplace transform we denoted it with the Laplace transform of f of t is equals to f bar of s, otherwise capital F of s. Okay. Now how we are going to denote this inverse Laplace means L inverse of f of s, otherwise f bar of s, any one notation. Okay, so here if you observe Laplace transformation of the function in terms of t gives a result in terms of s. Here the given function will be in terms of s and the resultant function will be in terms of t. Okay, so inverse Laplace transformation is denoted as L inverse of f bar of s is nothing but f of t. Okay. And next, so as we have learned about Laplace transform of 1 as 1 by s and Laplace transformation of e power at as 1 by s minus c. Now here it's reciprocals, like inverse Laplace transformation of 1 by s is equals to 1 is defined, and similarly inverse Laplace transformation of 1 by s minus a is e power at means exactly whatever the function for which function we have applied Laplace and we got some certain f bar of s, right? That f bar of s becomes a question function here, and their f of t is then that f of t will be a resultant function in this inverse Laplace. So previously what we have learned is like Laplace transformation of e power at is nothing but 1 by s minus a. So now here the same thing will be in a reverse manner learned as inverse Laplace transformation of 1 by s minus a is equals to e power at. Okay, right. So therefore, in the same manner, if we go with the inverse Laplace transformation of remaining all standardized functions, like 1 by s power n is defined as t power n minus 1 divided by n minus 1 pi to L when this n value starts from 1 and 2, 3 and continues. But because for n, if n is negative, negative of factorial is not defined, so n is not negative in this case. So next, inverse Laplace transformation of 1 by s minus a whole power n is defined as e power at into t power n minus 1 divided by n minus 1 factorial. And inverse Laplace transformation of 1 by s square plus b square is 1 by b into sine bt. Similarly, inverse Laplace transformation of s by s square plus b square is cos bt. And 1 by s square minus a square is 1 by into sine hat. And inverse Laplace transformation of s by s square minus a square is cos hat. Inverse Laplace transformation of 1 by s minus a whole square plus b square is 1 by b into e power at into sine bt. Okay. Similarly, inverse Laplace transformation of s minus a divided by s minus a whole square plus b square is e power at into cos bt. Inverse Laplace transformation of s by s square plus b square whole square is 1 by 2b into t into sine bt. T into sine bt. So with the help of these standardized formula, we are going to solve the sums in inverse Laplace transformation. So let us see a few examples how to resolve this inverse Laplace transformation of the given functions. So find the inverse Laplace transformation of the given functions. So what are the given functions here? 6 by s plus 1 by s minus a plus 4 by s plus 3. Okay. So what happens again here also linear property of inverse Laplace transformation is applied. So inverse Laplace operator, if you apply inverse Laplace operator here, then that inverse Laplace operator will be separated for all the terms. Like inverse Laplace transformation of 6 by s plus 1 by s minus 8 plus 4 divided by s plus 3. So inverse Laplace operator will be separated for all the three terms here. Then it will be written as inverse Laplace transformation of 6 by s plus L inverse of 1 by s minus 8 plus L inverse of 4 by s plus 3. And separately, if we try to find out their respective inverse Laplace operators, in the inverse Laplace operator of 6 by s is 6, inverse Laplace transform of 1 by s minus 8 is e power 80, and inverse Laplace transform of 4 by s plus 3 is 4 into e power minus 3t. And if I add them together, we are going to have our required f of t. So this is our required first example. Okay, so what we have done, we have calculated inverse Laplace transform of 6 by s plus 1 by s minus 8 plus 4 by s plus 3. Individually we calculate, otherwise directly also we can write their respective functions. Second example, let us see. So here how many terms we are going to have? Inverse Laplace from 3 terms. First one is 19 divided by s plus 2 plus 1 divided by 3s minus 5 plus 7 divided by s power 5. Okay, so s power 5. Next, by using again linear property formula, this inverse Laplace transformation will be separated for all the three terms like this. So thereafter, now let us find out the inverse Laplace transformation by using the respective formula. So here the 19 can be kept outside. Inverse Laplace transform of 1 by s plus 2 is e power minus 2t. Okay, so similarly 1 by 3s minus 5. So actually we doesn't have any sort of formula for this 1 by 3s minus 5. So what we have to do, we need to take 3 common out of this 3s minus 5. If we take 3 common, s minus 5 by 3 will be there. S minus a format. Okay. So this 1 by 3 is kept outside the inverse Laplace operator, and the function is now remaining 1 by s minus 5 by 3, which is nothing but e power 5 by 3t. So next 1 by s power 5. 1 by s power 5 is inverse Laplace transformation of 1 by s power 5 is nothing but 5 factorial divided by t power 5. Okay. So therefore here it's n minus 1 factorial. So 4 factorial divided by t power 5. So for 4 factorial will be written here. So 7 is already outside. There is no 4 factorial here. So 7 into 4 factorial divided by s power 5. They have written actually. They multiply and divided with 4 factorial. Otherwise, we can directly write that as 4 factorial by t power 5. Okay. So which implies inverse Laplace transformation of 7 divided by s power 5 is equals to inverse Laplace transformation of multiply and divided with 4 factorial is defined as like 7 by 4 factorial into t power 4. Okay, so like this we can evaluate inverse Laplace transformations for the given standardized functions. So after this you see, so here are these examples. So we can consider few more examples also. Inverse Laplace transformation of 1 by s square plus 1 by s minus 1 plus 3 into s by s square plus 4. So what happens according to linear property? Again, we need to separate this L inverse for all the three individual terms. L inverse of 1 by s square plus L inverse of 1 by s plus s minus 1. Okay, plus 3 into L inverse of s by s square plus 4. Which implies 1 by s square is defined for t, and this is e power t, and the next one is 3 into cos 2t. So like this, we can calculate f of t for the given f of capital F of s, otherwise f bar of s. L inverse of f bar of s is nothing but f of t, right? So like this, we can evaluate many functions by applying inverse Laplace transform. Okay, so this is all about inverse Laplace transformations. So the only thing what we are supposed to do is we need to memorize our required standardized formulae. That is inverse Laplace transformation of 1 by s is equals to 1 and so on. So inverse Laplace transformation of 1 by s minus a is e power a t. Inverse Laplace transform of 1 by s power n is t power n minus 1 by n minus 1 factorial and so on. Okay. Okay, so with this video, we completed the basic information about the inverse Laplace transformation and how to evaluate inverse Laplace transformation for the standardized functions. Okay.